Whether you are furiously prepping for a highly technical data science meeting right now, or maybe you just have this kind of insatiable curiosity about how modern artificial intelligence actually makes decisions under the hood, today's deep dive is designed specifically for you.
Yeah, we're looking at a system that basically takes pure injected chaos and somehow, against all logic, turns it into razor-sharp insight.
Right. It genuinely pushes the boundaries of how we think about problem solving. I
Yeah.
mean, we are trained to think that adding randomness to a logical process degrades it.
Oh, absolutely. But in this case, throwing blindfolds and intentional noise at an algorithm actually forces it to become significantly more precise. It's fascinating.
It really is. So today, our mission is to completely demystify this foundational machine learning method. We are using a really comprehensive Wikipedia article on the random forest algorithm as our source material.
And there's a lot to cover in there.
Oh, tons. We're going to explore how this evolved from a theoretical concept in the 90s into this mathematical powerhouse. We'll unpack the notorious black box of how it evaluates its own decisions. And we're also going to reveal some truly surprising hidden connections it shares with entirely different algorithms.
Yeah, the connections to other machine learning concepts are probably my favorite part.
Same here. Okay, let's unpack this. And to do that, we have to start with the fundamental building block. Because before we can talk about a forest, we need to look at a single decision tree.
Right, because the entire genius of the forest only makes sense once you understand the fatal flaw of the single tree.
Exactly. Now, decision trees themselves are incredibly popular. The source material notes they are essentially the standard, off-the-shelf procedure for data mining.
For good reason, honestly.
Yeah. For one, they are invariant underscaling. You don't have to perfectly normalize or standardize all your data to tight little ranges before you feed it in.
Which saves a massive amount of pre-processing time.
Right. And they are also incredibly robust against irrelevant features, and maybe most importantly for developers, they produce highly inspectable models. You can visually trace the path from the root node all the way down to the leaf and see exactly the logic the model used.
The interpretability is a massive selling point. But there's a catch. As researchers Hasty, Tibshirani, and Friedman point out in the text, there is a severe limitation. They are, in their words, seldom accurate.
Which is obviously a catastrophic problem for a prediction model.
Yeah, a bit of a deal breaker. The core mathematical issue arises when these trees are grown very deep.
What do you mean by deep exactly?
Well, when a decision tree is allowed to keep asking questions, just making splits all the way down until it has isolated almost every individual data point, it begins to learn highly irregular, idiosyncratic patterns.
Ah, I see.
In machine learning terms, this is described as having low bias but very high variance.
I was thinking about this high variance problem, and it feels like a student who perfectly memorizes a specific practice test. Like they know that on page 3, the answer to the second math problem is 42.
Right, they just memorize it.
Exactly. So they get 100% on the practice test, but then they completely bomb the actual final exam because they didn't learn the underlying mathematical formulas. They just memorized the specific noise and the quirks of that one practice test. They overfit.
That is a perfect analogy. If we look at the math behind that overfitting, the tree isn't finding the true underlying signal of the data. It's just drawing incredibly jagged, complex boundaries around the noise it was trained on.
So it's hyperfixating on the wrong things.
Exactly. So if you feed it slightly different training data, the resulting tree looks completely different. That instability is the variance.
Which brings us to the actual topic today.
Right, and that leads us to the core thesis of the random forest. The goal is to take multiple deep decision trees.
These over-memorizing students.
Yes, take a bunch of those students, train them on slightly different variations of the same data, and average their predictions together. You sacrifice a tiny bit of bias, and you completely lose that lovely interpretability, but you violently drive down the variance.
Wow. Okay. So we move from a single overfitting tree to planting a whole forest. But if we trace the evolution of this idea, the source notes, it didn't just happen overnight, right?
No, not at all. It took years of theory.
Right, because back in 1995, researcher Tin Kam Ho created the first algorithm for this using something called the random subspace method. And she was actually building on even earlier theories by Eugene Kleinberg called stochastic discrimination.
Yeah, the core realization there was that if you restrict what an algorithm can see...
Like literally blinding it to certain parts of the data.
Exactly. If you blind it, it actually gets smarter. And that idea was later expanded upon by Leo Breiman, who introduced a core mechanism that makes modern random forests work. And Adele Cutler was involved in extending this too. Bryman and Cutler actually trademarked random forests in 2006.
Oh, wait, it's trademarked.
Yeah, currently owned by Minitab Inc., but the core technique they popularized is called bagging, which is shorthand for bootstrap aggregating.
Okay, let's break down how bagging actually works mechanically.
Sure. So if you have a training data set, say 1,000 rows of data, the algorithm doesn't just hand all 1,000 rows to every tree.
That would just make identical tree.
Right. Instead, it repeatedly samples that data with replacement to build a unique training set for each individual tree.
Wait, with replacement, meaning it's like drawing names from a hat, but after you draw a name and write it down, you put this slip of paper back into the hat before you draw again.
Correct. Because you are putting the data points back, a single tree's training set might contain duplicates of certain rows while completely missing others.
Ah, okay. That introduces some randomness.
Exactly.
Okay.
Statistically, drawing with replacement means each tree only sees about 63% of the unique data points from the original set. The remaining 37% are left out entirely for that specific tree.
Okay, I actually have to push back on this logic for a second.
Go for it.
Even if we are sampling with replacement and shuffling the rows around, we are still generally feeding the same overall massive data set to a bunch of trees. If there is one incredibly dominant pattern in the data, won't every single tree just latch onto that exact same pattern first?
That's a very valid concern.
Right, like they'll all look slightly different at the bottom, but the core decisions at the top will be identical, so averaging them won't actually help that much.
What's fascinating here is that Bryman anticipated that exact bottleneck. If you just use standard bagging, the trees remain highly correlated. They all make the same primary mistakes.
So how do you fix it?
The solution to break that correlation is called feature bagging.
How does feature bagging change the math?
Well, standard bagging samples the rows of your dataset. Feature bagging samples the columns, the variables themselves.
Oh, I see.
Yeah, at every single node where a tree is trying to decide how to split the data, the algorithm steps in and says, no, you cannot look at all the features. You can only look at this small, random subset of them.
Wait, really? How small of a subset?
For classification tasks, it typically restricts the tree to a subset equal to the square root of the total features. For regression, it's usually about a third.
Oh, wow. I see the mechanism now.
Yeah.
Let's say we're trying to predict if it will rain, and one feature is the sky is completely black.
Right.
That is a massive dominant predictor.
The most obvious one, yeah.
Right. Without feature bagging, every single tree would just split on black sky right at the top node. They would all become clones of each other.
Exactly. By forcing the trees to look at random, restricted subsets of columns, you effectively decorrelate them. You force some trees to figure out how to predict the rain without being allowed to look at the black sky variable at all.
That's brilliant. So they have to find secondary, tertiary, and completely hidden patterns in, like, the humidity or the wind direction.
You got it. When you average those uniquely constrained, highly diverse trees together, you create a true wisdom of the crowd effect that is far more resilient than any single tree.
That is incredibly clever. Okay, so now we have a functioning forest. It's making highly accurate predictions by combining all these uniquely constrained trees. But human beings are naturally distrustful of black boxes.
Oh, of course we are. We want to know the why.
Right. If I feed a massive data set into this, I don't just want the final prediction. I want to know how the forest arrived at it. Like if I'm using this for medical data, I don't just want to know if someone is sick. I want to know which symptom was the biggest red flag, which clues were actually driving the math.
Well, random forests have built-in mechanisms to rank variable importance. The first and arguably most robust method originally outlined by Bryman is permutation importance.
Permutation, okay.
Remember a moment ago when we talked about the bootstrap bagging process? How drawing with replacement naturally leaves out about 37% of the data for any given tree.
Right, the hat drawing method means some rows never get picked for tree number 42.
Exactly. Those left-out rows are called the out-of-bag samples. They are incredibly valuable because they act as a built-in testing set.
Oh, built-in testing. That's handy.
Right. To figure out how important a specific feature is, say, blood pressure in a medical data set, you first run those out-of-bag samples through their respective trees and record the baseline prediction error.
Okay, establishing a baseline.
Then you take the blood pressure column in those out-of-bag samples and you randomly scramble all the values. You permute them.
Wait, you essentially break that specific column of data on purpose to see what happens.
You break it, and then you run those scrambled samples through the trees again. If the error jumps up massively, it proves that the model was heavily relying on blood pressure to make accurate predictions. It's highly important.
And if it doesn't jump?
If the error barely changes, it means the model wasn't really using that feature anyway.
Okay, so permutation breaks the data intentionally. But didn't the tree already do a massive amount of math on which features were best when it was initially calculating the splits? Can't we just look at its own homework to see what it valued?
We can, actually, and that is the second built-in method, mean decrease in impurity.
Mean decrease in impurity, okay.
When a tree is building itself, it evaluates a split by seeing how cleanly it separates the classes. Imagine a node with 10 patient records. If a split divides them so one side has 9 sick patients and the other have 1, that is a very pure split.
Right, it effectively segregated the data into distinct categories.
Exactly. And the algorithm measures this purity using mathematical metrics like the Janet coefficient, entropy, or mean squared error for regression.
Okay, and then?
Mean decrease in impurity simply tallies up how much a specific feature reduced the impurity across every single split it was involved in, across every tree in the entire forest.
Oh, that makes sense.
It's incredibly fast because, as you said, it's just aggregating the homework the algorithm already did during training.
So what does this all mean for the end user? It means you have two distinct tools to peer inside the black box. But I imagine they aren't flawless.
No, they both have significant drawbacks. Permutation importance unfairly favors features that have more distinct values.
Oh, really?
Yeah, and it breaks down when you have collinear features, variables that are highly correlated with each other, like height and leg length.
Right, because if you scramble one, the model just leans on the other.
Exactly, making both look less important than they actually are.
And what's the catch with the impurity method?
Impurity metrics, which happen to be the default in popular programming libraries like scikit-learn, suffer from high cardinality bias.
High cardinality meaning like variables that have a massive number of unique values, like an ID number or a zip code.
Exactly. The math of the Janet coefficient naturally favors features with lots of unique values, inflating their importance artificially.
That sounds dangerous.
It is. Worse, impurity importance only reflects statistics gathered during the training phase. It does not necessarily reflect how useful a feature will actually be when the model is hit with new, unseen test data out in the real world.
Wow. That is a huge caveat for any data scientist to keep in mind. Okay, we've opened the black box, we've scrutinized the variable importance. Now I want to step back and look at the algorithm's DNA.
Let's do it.
Because the source material reveals that this supposedly unique ensemble of trees is secretly related to other foundational machine learning concepts.
This is where the theory gets genuinely beautiful. Let's look at the relationship to k-nearest neighbors, or KNN. In 2002, researchers Lin and Jine mathematically proved that random forests and KNN are actually both operating as weighted neighborhood schemes.
Now, standard k-nearest neighbors is pretty intuitive. It essentially says, tell me who your neighbors are, and I'll tell you who you are.
Exactly.
If you plot data on a graph, KNN draws a rigid physical boundary around a new data point and looks at the closest physical neighbors to classify it.
But Lin and Jan realized a random forest is doing the exact same thing, just with a fundamentally different definition of what a neighbor is.
How so?
Well, instead of looking at physical Euclidean distance on a graph, a random forest defines a neighbor as a data point that ends up in the exact same final leaf node of a decision tree as you do.
Oh, that is a fascinating shift in perspective. It's like finding out your two completely separate groups of friends actually hang out without you.
Yeah.
KNN and random forests approach it so differently, but arrive at the same concept.
It really is.
Standard KNN is like drawing a rigid physical circle around your house and saying, everyone in this geographic circle is my neighbor. But a random forest defines a neighbor by shared traits. You both like jazz, own golden retrievers, and work night shifts. The neighborhood isn't a physical circle. It morphs dynamically based on what traits actually matter to the trees.
This raises an important question, though. Why is the forest's version of a neighborhood often mathematically superior?
Yeah, why is it smarter?
Lin and Jian showed that because the random forest adapts the shape of its neighborhood based on the local importance of each feature, it doesn't get confused by irrelevant noise. It only groups you with data points that share the characteristics that are actually driving the outcome.
You know, we've been talking about this whole process, assuming the forest knows what it's looking for, that we've handed it data neatly labeled with the correct answers during training.
Right, supervised learning.
But the real superpower, mentioned in the source, is that it doesn't always need us to hold its hand. It can operate completely in the dark, performing unsupervised learning.
Oh, this is such a cool trick. You can effectively force a random forest into working without any labels at all.
How?
You do this by generating a massive set of synthetic data. You take your real data and you independently shuffle the values in every single column. This totally destroys any underlying structure or correlation between the features.
Okay, so you make a garbage data set.
Right. Then you ask the random forest to classify whether a data point is from the real set or the shuffled synthetic set.
So it's forced to learn the deep structural rules of the real data just to distinguish reality from random noise.
Exactly.
The source mentions this creates a dissimilarity measure called ADCL1. What exactly is that math doing?
ADCL1 basically tracks how often two real data points end up in the same leaf node, while the forest is trying to separate the real data from the fake data. If two patient records constantly land in the same leaf node, the algorithm mathematically concludes they are highly similar, even if it doesn't know what disease they have.
That's wild.
Because random forests handle messy, mixed variable types effortlessly, this specific dissimilarity measure has been famously used to find hidden clusters of patients based on incredibly complex tissue marker data. It handles outliers beautifully, too.
Amazing. Well, if random forests are this versatile and this mathematically adaptable, what happens when researchers push the logic to the absolute extreme?
You get some highly theoretical boundary-pushing variations. One of the most striking is extra trees, which stands for extremely randomized trees.
Here's where it gets really interesting to me. In standard random forests, we've established that we inject randomness by sampling the data rows and restricting the feature columns. But when a tree actually sits down to make a split, it calculates the perfectly optimal, mathematically best cut point for that specific feature. Extra trees throws that optimization completely out the window.
It abandons it entirely. Extra trees doesn't even bother with bootstrap bagging. It uses the whole learning sample. But for the feature splits, it picks completely random cut points.
Wait, just totally random?
Totally random. It just blindly guesses a few random split values for a feature, tests them, and picks the best of those random guesses, rather than calculating the true optimal split.
It's so ironic. You add even more noise. You literally strip away the algorithm's ability to find the mathematically perfect split, and it still yields highly competitive, incredible results. It proves just how much heavy lifting the ensemble averaging is actually doing.
It really does. Then you have researchers tackling the nightmare of high-dimensional data. If you feed a random forest thousands of features, but only 3 of them are actually informative, the forest can drown in the sheer volume of noise.
Because the random feature subsets will almost always be filled with garbage variables.
Exactly.
So how do you fix the math when the noise outnumbers the signal?
Several ways. There is pre-filtering, which is simply using a separate statistical test to strip out the garbage variables before the forest even sees them. Then you have enriched random forests.
Think of an enriched random forest like a rigged lottery. Instead of every feature getting an equal number of ping pong balls in the drawing machine, the algorithm identifies the historically smarter features and gives them extra balls.
That's a great way to picture it. It uses weighted random sampling to increase the odds that the good features get selected for a split.
Right.
And similarly, there are tree-weighted random forests. Instead of treating every tree in the forest as an equal voter, you treat it like a corporate boardroom.
Where some votes matter more?
Exactly. The trees that prove to be highly accurate on the out-of-bag samples get more voting power in the final prediction than the mediocre trees. But, if we are talking about extreme mathematics, the biggest theoretical leap is KERF, the kernel random forest.
Now, if you're listening to this and wondering why we are suddenly talking about kernel methods in a decision tree deep dive, bear with us, because this is the bridge between dirty, real-world data and elegant math.
Yes. If we connect this to the bigger picture, KERF isn't just a party trick. It's a massive theoretical breakthrough.
How so?
Well, kernel methods are rigorous mathematical tools used to map data into infinitely higher dimensions to separate it. They are theoretically beautiful and allow mathematicians to prove concrete guarantees about an algorithm's performance.
Okay, and trees.
Decision trees, on the other hand, are gritty, discrete, and computationally messy. They work practically, but they are hard to analyze mathematically.
But Leo Breiman noticed a link, and a researcher named ScoreNet formally defined it, right?
Yes. ScoreNet modified the definition of a random forest slightly, creating the centered kerf and uniform kerf. By doing this, he proved that random forests can actually be rewritten mathematically as kernel methods.
Wow.
And because he built that bridge, he was able to mathematically prove the upper bounds on their rates of consistency.
Meaning He could mathematically guarantee that given enough data, the forest will actually converge on the absolute truth. It isn't just a computational hack anymore, it is theoretically sound.
Exactly.
So we've built this incredibly robust, mathematically guaranteed, highly adaptable forest. It handles noise, it gives us variable importance, it bridges massive theoretical gaps in machine learning. Which brings us to the inevitable catch.
There's always a catch.
If it is this powerful, why isn't it the only algorithm developers ever use?
First, we return to the massive loss of intrinsic interpretability. We talked about variable importance tools earlier, but those only tell you what mattered. They do not tell you how the specific decision was made. Following the path of a single decision tree is trivial. Following the intersecting paths of 500 deeply randomized trees is physically impossible for a human mind.
Imagine trying to explain to someone why they were denied a bank loan. If you use a single decision tree, you can say, well, your credit score was below 700 and your income was below this specific threshold, so the math says the loan is denied. It's a clear, understandable why.
Which people need.
Exactly. But if you use a random forest, you basically just have to give them the collective shrug of 500 trees. The forest has spoken. You can't explain the exact path, and when end users can't understand a model, they lose trust in it entirely.
And there are genuine performance drawbacks, too. If your underlying data features are perfectly linearly correlated with your target variable, a random forest might actually perform worse than a basic, computationally cheap linear model like a multinomial logistic regression or naive Bayes.
Overkill, essentially.
Yeah, and it also struggles heavily when dealing with multiple categorical variables that have completely different numbers of levels.
But the source material notes that researchers have found a brilliant solution to the interpretability problem. If the massive forest is too opaque, they use model compression.
Yes, they transform that massive, impenetrable random forest back into a minimal, single decision tree. They call it a born-again tree.
Wait, how does a single tree replicate a whole forest without just reverting to the overfitting problem we started with?
Because the born-again tree isn't trained on the original noisy data. It is trained to perfectly reproduce the exact decision function of the massive ensemble.
Oh,
It learns the smooth, variance-reduced logic of the forest, but compresses that complex logic into one human-readable tree structure.
that is the ultimate having your cake and eating it too scenario for a data scientist. You reap all the predictive power and get all the mathematical variance reduction of the massive random forest, but you hand the end user a perfectly interpretable single born-again tree.
It is a profoundly elegant full-circle moment for the algorithm.
It really is.
Yeah.
So, to recap our journey today, we started with a single overfitting tree, our student memorizing the noise of the test. We multiplied it.
We injected intentional randomness through bootstrap bagging and feature subsets to decorrelate the errors, making the crowd significantly wiser than the individual.
We peeked inside the black box using permutations and impurity metrics to find which variables mattered most. We explored its hidden, shape-shifting connections to k-nearest neighbors in kernel math, and finally, we compressed all that messy collective wisdom back down into a single, understandable, born-again tree.
It is a masterclass in how embracing a little controlled chaos can actually lead to much clearer, more robust answers.
Absolutely. And it leaves me with one final thought to chew on. We've spent this time seeing how we can take the messy, deeply randomized, noisy collective wisdom of a massive random forest and mathematically distill it into a single, perfectly interpretable, born-again rulebook.
Yeah.
Could we ever do the same with human systems? Imagine if the chaotic, decentralized, incredibly noisy decisions of a whole society could somehow be mathematically distilled into a single, perfectly logical set of understandable rules. It makes you wonder if our own chaotic processes are just waiting for the right mathematical algorithm to compress them into clarity. Thank you for joining us on this deep dive into the source material. Stay curious.